Svalbard, in the Norwegian High Arctic.
This archipelago is one of the few places on our planet where you can see the effects of climate change unfolding in real time. The Arctic is warming 4 times faster than the rest of the world. Svalbard is warming faster still, as much as 7 times the global average. Here, dying glaciers, thawing permafrost, and disappearing sea ice are clear indicators of climate warming. The over 2,000 permanent residents of Longyearbyen, the world's northernmost town, are having to adapt as their tap water becomes undrinkable due to minerals and metals like manganese released by thawing permafrost. But this is not just a local issue. The implications of Arctic climate change ripple far beyond the region.
The context of Svalbard is really important. We're lying next to the North Atlantic system. We've got a lot of energy and a lot of heat and associated oceanic currents bringing energy up here. So we're right on the boundary of a very rapidly warming part of the Arctic here. So it makes good sense to come here and treat Svalbard as the kind of canary in the coal mine for high Arctic change. So it's still quite cold back in the 90s. But it has been pretty much a year-on-year warming since, with some, minor aberrations. But really, it's the last 10 years where it's really unabated warming and impacts, glaciers clearly changing shape and changing their dynamics, snow cover and sea ice loss, really, really noticeable over the last 10 years.
It's really interesting as a scientist here to see firsthand these changes. Of course, I'm a cryosphere science, so I'm interested in permafrost and glacier interactions. And some of the main changes that we're seeing in permafrost is deepening of the active layer. So the active layer is the layer that sits on top of permafrost that freezes and thaws on an annual basis. And that layer is increasing. It's the summer thaw layer everywhere on the landscape is just getting deeper and deeper. So every year there's a new opportunity for manganese, iron, pyrite oxidation to produce new problems with the surface water system. In the last few months in Longyearbyen, we've seen an increase in manganese levels in the drinking water. Manganese has been raised or flagged as the main issue here because it's above threshold quantities that are safe for drinking water. So one of the challenges in CryoSCOPE is to try and assess how we're having more and more groundwater exploiting these flow paths with access to new mineral resources caused by thaw, and to assess how important they are for deteriorating water quality.
As part of the CryoSCOPE project, the UNIS team has set up a field observatory on the forefield of the Skotturnabreng Glacier. Here they can see firsthand the interactions between a retreating glacier, permafrost formation, and the emergence of new groundwater springs.
So Skotturnabreng is just visible up there, more or less. It's hard to see actually today. It's actually lost 90% of its volume in the last 100 years. And one of the reasons is this unwanted harmful advance just as the climate got warmer. So here we are behind a moraine ridge and a very flat floodplain here, and the glacier behind it. And this is precisely one of those locations that's being exploited by groundwaters.
So we're right now in the Skotturnabreng forefield, and we're at the location where the groundwater springs emerges from the ground. And so you can actually see there's liquid water right here. And the middle of winter at -5. So I think it's quite exciting to see the location of where this groundwater spring comes out. We don't have yet permafrost closing the cryospheric cap here at this location, so it manages to emerge and flow through these gravels into the forefield. So this here is a borehole, or at least what's coming out of the surface. This borehole was drilled in this moraine, 20 meters deep, and instrumented with a thermistor string, where we're measuring the ground temperatures at different depths. We have installed a borehole in a location where we know it's forming, versus a location where we think there's groundwater flow, so we can compare both. And so here at this site, the ground is actually a few degrees colder than just 200 meters further down where the water's flowing. So we can now successfully say that there's permafrost at this site and not at the lower site.
So through CryoSCOPE, we can actually use all these instruments here and these measurements to constrain numerical models that help us better understand some of these sort of almost unstoppable natural responses to the climate-driven change here. And so, yeah, we're putting a lot of time and effort, and then we'll be employing people to run, the state of the science numerical models to represent the how the glacier retreats and how the permafrost tries to form as the glacier retreats, and how the groundwaters carry lots of climate-relevant gases like methane and exploit that area in front of the glacier as it retreats.
To get an understanding of the bigger picture, you have to journey deep inside the glacier itself, where the passing of the seasons and the changing climate are etched into icy channels carved out by meltwater cycles over the centuries.
So we're inside Scott Turner Brain now, and then we're in one of the many channels that's just cutting down every summer. These are called cut and closure channels, because usually they cut down and then the tops close over, maybe with a little bit of ice flow or by getting blocked by snow. So through a channel like this, we typically have a discharge of about 1 meter cubed every second. During July, that's about a ton of water every second. So you can imagine that this is full of water, nearly full anyway, and then every year it gets deeper and deeper, and it migrates in 3 dimensions, meandering and eventually cutting all the way to the bottom. And this is what's happening. Bigger and bigger flows during the summer makes these channels larger, and they cut deeper and deeper. So really changing the way that water drains this landscape. So we found that the gas emissions at the ice margins due to these groundwaters is the single largest methane source to the atmosphere that's coming from Svalbard. There's a lot of methane from elsewhere in the Arctic that's being blown over the island as well. So that means we have a kind of unstoppable greenhouse gas leak forming that we need to account for, because maybe we have to manage our methane emissions better elsewhere, and we certainly have to do that. We're not, that's the problem. We can't stop these fluxes, but we can actually control our own emissions better, and knowing by how much we have to do that is useful.
I think one of the main take-home messages from our project is that understanding the different components in the cryospheric systems can help make more informed-based decision-making, where if we understand why there's high manganese levels in the Longyearbyen drinking water and link it back to an earth process, it actually can help inform other places where you would find similar issues.
There's the old adage that what happens in the Arctic doesn't stay in the Arctic necessarily. It's well known that warming here is having an effect in the mid-latitude systems, and it is now proving costly. So given what we are seeing here, we're just kind of trying to get the message across to the relevant policy-making authorities that things here are hard to manage, but where you are, it's actually a lot easier, so effect those changes where we can, and then let's just keep a track on what's going on up here.
The CryoSCOPE project brings together research efforts in 10 field sites across 6 of the world's most vulnerable frozen regions. The study of these landscapes is crucial for the understanding of the climate system and hydrological cycle. For more, go to cryoscope-project.eu.